So here's an introductory thing for class 2. We're still dealing with the kinematics of particles. Now we're going to deal with constant velocity, constant acceleration, and dependent motion. Those are the main topics that we're going to cover today. And so here's the equations that we're going to work with, or here's the equations on your equation sheet that really emphasize or are the main aspect of this particular class. So you can see, and these are ones that you probably had in physics. You've probably seen these in physics and even in high school and various, I don't know, physics class, but also maybe just like any kind of like earth science class or something along those lines. And they're only applicable when either velocity is constant, which they're saying uniform translational motion right here, or when acceleration is constant, which is these guys right here. Right? And they're written. I've written them in vector form, but also just in scalar form if we're just dealing in one direction. We also have relative motion, which is it looks easier than it is deceptively easy, but we'll take a look at that. And the consequence of this relative motion, we could also have something dependent motion, and we refer to those often as pulley problems, and students will struggle with those. So that's an important thing, and I think I'll have a separate video when I do the introduction. So we're really going to deal in this video with constant velocity and constant acceleration. And I'm missing a quote right in there. Okay, so these are really special cases of motion, and this is section 11.2 at Beard Johnston, by the way, 11.2a, where we have constant velocity. So that means the acceleration as a function of time is 0. No kidding. So the velocity as a function of time is equal to a constant. And if we want to, we'll give it a subscript c. Whoops. I'm sorry, I was writing that over here. Yes, there you go. I'm going to keep it because I can't just redo these videos every time I have making too many of them. So at constant velocity, the acceleration as a function of time is 0. So the velocity is constant, and we could write that as vc. So velocity is dx dt. So we rewrite this as dx is equal to v dt, right? And then we can take the integral of both of those things, and we'll say that we'll call that x 0 or x naught sometimes, right? There's where it starts. Here's where it ends, or it doesn't necessarily end. We're really, a lot of times we're just trying to find a new function, right? So that we can write down an equation that's useful to us. And here's the velocity. Whoops, I messed up right there. Should be the time. Time 0. We'll often make this, because we can start our watch anytime we want, often will be at 0 right there. And we know that this velocity now, though, is constant. So he could actually come to the outside of this, and what we're left with is x minus x0, that integral over there, is going to be equal to vc times t, right? Because there's 0 right here. We don't want to worry about that. So that's a very simple problem. So we can say that x is equal to x naught plus vc times t. And in your book, that's equation 11.5. We have to be careful. Many students, engineers, many even working engineers get into this bad habit of hunting for equations in books, and until they find the equation that jumps out at them, like, this has all the variables that I need in it. But you want to be careful that this is specifically to the constant velocity case, and you'll see throughout your engineering career that you'll fall into this trap where you'll just be hunting for equations. But let's try to apply concepts instead of hunting for equations. So now this is for the special case of constant velocity. Now we have the special case of constant acceleration. So that means that acceleration as a function of time is constant. And if we remember to do it, we could put him with a subscript c, just to say that he's constant. So we could have several different equations that are going to fall out of looking at this. If we say the acceleration is, let me go dv dt first. Right? And I draw a little arrow right there, and now I can rewrite this thing as a dt, but he's constant. So if we like integrate this from v naught to some velocity, right, and integrate this from time 0 to t, we just end up with the simple equation, and I'll just rewrite the thing out. The velocity, right, is going to be equal to, because this one would be minus over here, it'll bring him over here, the original velocity plus the acceleration times time. You can see how that works out, right? So right here, that is equation 11.6. Now, this now has velocity as a function of time, right? So we could use this one again to find position, right? Because we know that velocity is equal to dx dt, and we're just saying x here just as some position. Could be in the y direction, could be in the z direction, could be r, whatever. It's just we're moving along a straight line. It doesn't have to be all in one direction. It can move back and forth, but it's a anyway. So I rewrite this one and say dx is equal to v dt, and we can integrate from the original position to the final position, or to whatever, this is just a generic position, and we can start from time 0 to some time. And what we end up finding here when going through this right here, we'll say that x, I'm going to bring this minus x over to the other side right over here, and integrating this right here. Oh, I needed to substitute that in. Okay, so let me not skip that step. Substitute him back in. The integral of v naught plus ac t dt, right, starting from 0 to t, right? That was important to put him into there, right? We can now say x is equal to x naught, which we just going to bring this over to the other side because it was minus x on that left side, and this becomes plus v naught times t plus, and now that's, we're integrating ACT, so that becomes 1/2 ACT squared. And now this is position as a function of time, right? Everything else in here, this is a constant, that's a constant because that's the original conditions. Acceleration is a constant, so we have t and t, they're just a function of t. And there you go, that's equation 11.7. All right, so we got one more though. This is the wild card that can take place. Remember that acceleration can also be expressed as dv is v times dv dx, right? So what we could do is we take acceleration, which remember is constant, times dx is equal to v dv. Integrate this from x0 to x and from v0 to v, right? And just from this right here, we could say that we have AC times x minus x naught, right, is going to be equal to 1/2 v squared minus v0 squared. So we can write out, move these things around here, say v squared is equal to v naught squared plus 2, because we're taking that and multiplying it over here to that side. 2 times, AC times x minus x naught. And so this is equation 11.8. These are worth memorizing, these fundamental kinematic relations when in special cases of constant acceleration and constant velocity. We'll see that we're going to use these in projectile motion. I think I'm going to have that in class 3 instead of in class 2. But these are easy equations to use at the wrong time, right? So you got to make sure that the special case of acceleration being constant is the only time that you use this. So you really have to, when you look at a problem and you recognize it's kinematics, particle kinematics, now you have to look really closely, be on the lookout for it, the acceleration being something that can change. Only when it's constant can you use these. So that, I think, is enough of a video. Let's see, what was our time on this? Yeah, 11 minutes. That's digestible.